Hey guys, today we're going to focus and talk about resistance. Resistance is caused by the free electrons that are flowing in a wire colliding with the atoms of the wire. And in the wire, resistance can affect the flow of current through the substance. Resistance causes the electrons to experience friction, which causes the conductor to heat up. So this diagram at the bottom shows us an example of molecules in a metal wire. And the electrons that flow through that wire have to flow around those molecules. They can't just fit straight through, they actually have to kind of follow a little path, and they have to create that path. Now notice two electrons may not follow the same path, but they always have to try to go around those atoms or those molecules in order to get through the wire. As this happens, every time that the electron moves and it bumps into a molecule, it causes a little bit of heat to build up. So when we have electricity running through wires, they feel warm or hot to the touch after a while, which is why they are covered in rubber. That rubber insulates them so it doesn't affect the surrounding areas. So resistance is the slowing of electrons based on the molecules in the wire as the electrons travel through the wire. There are other things that affect resistance. So these four things I'm going to talk about briefly, and hopefully it'll make sense. The length of the wire affects the resistance because the longer the wire, the higher the resistance is. If you think of a hallway, the longer the hallway, the longer amount of time it takes for you to travel through it. You're trying to make your way past all these little molecules, and if there is a longer length of wire, there's automatically more molecules to travel through. The next thing is the cross-sectional area of the wire. And all that means is that if we look at the wire from the end, how large is it? So we can have a little skinny wire, we can have a medium wire, or we could have a huge wire. Just like straws, this has the same idea. If you want to drink some pop, this middle straw would be a good straw to use because you're still going to get liquid traveling up it. If you wanted to drink a milkshake, you would choose this straw, which is much larger. So if you have a larger cross-sectional area, you have more options of locations that you can travel, so it means that the current travels faster. So this first picture, it's a very skinny wire. You do not have very many options. You have to go in one straight path. This second picture, you have some more options. So this is a medium speed wire. This last one, it would be the fastest moving current because the wire is so wide. There are so many options to go through. Okay, the next thing is temperature. So when we talk about temperature, I like to use the game Wipeout on TV as an example. The higher the temperature is, the higher the resistance is. And this is because of how molecules move as temperature increases. So imagine trying to run across a balance beam while people are swinging pendulums across it. So if you're trying to move this way, but the molecules are swinging back and forth in front of you, if they're moving slowly, they're easier to dodge. The faster they move and the more crazy they move, the harder they are to predict, so it takes a while to move around them. So the higher the temperature, the more the molecules are moving, so the harder it is to move around them. The last one is resistivity. And resistivity is just the fact that every single substance on this planet has a different structure which affects how many or how fast electrons can flow through it. For example, if you have a high resistivity, a high value of resisting the moving of electrons, you're considered an insulator. That would be rubber. Rubber has a high resistivity, which is why it insulates our wire. A low resistivity means that there is a low resistance to flow. You would be considered a conductor. While copper is not the best conductor, it's one of the cheaper ones, so a lot of wire used in households is copper wire. So resistivity is different for every substance, and it's based on the substance and its molecular structure, and whether or not electrons can flow through them easily. So these four things have to be taken into consideration. Using this idea of resistivity, we can introduce something called Ohm's law. Ohm's law is the measure of resistance in ohms, which rhymes with homes, and it looks kind of like a horseshoe. It is a Greek letter, and that's going to be the unit for resistivity. So the formula for Ohm's law is V equals I times R. V is the voltage, I is the current, and R is the resistivity. Voltage is given in the unit of capital V, current is given in the unit of capital A, and resistivity is given in that horseshoe-shaped Greek letter. So when we calculate this, if we're solving for the V or the voltage, we're going to write down a number and put a capital V after it. If we're solving for the I or the current, we're going to write down a number and put a capital A after it. And if we're solving for resistance or ohms, we're going to write down a number and put this horseshoe shape behind it. Okay, so our first practice problem. What is the resistance of a lamp if it draws 0.25 amps from a 110 volt line? So just like normal, we have V equals, I equals, and R equals. V is 110, I is 0.025, and R is our question mark. So given our equation, we would have 110 equals 0.25 times capital R, divide both sides by 0.25, and capital R is 440 ohms. Not too bad, just simple algebra. Let's do one more. What is the current when a 5,000 ohm appliance is connected to a 110 volt line? So again, V equals, I equals, R equals. V is 110, current is my question mark, and R is equal to 5,000. I times R. Divide both sides by 5,000. And I is equal to 0.022 amps. Okay, so the first thing we're going to do is practice with this idea of resistivity and Ohm's law and do some math problems. So I'll see you in class so we can go ahead and do that.